Hello everyone, I am Usha, currently pursuing BTech final year in Electrical and Electronics Engineering at Tigala Krishna Reddy Engineering College. Today in this presentation, I am going to present my paper which is going to publish in 7th International Conference on Computing Methodologies and Communications. My paper is titled as Distribution System Power Quality Improvement Using IRP Theory. ICC-MC 139 is my paper ID. Coming to abstract, a shunt active power filter is suggested in this study. In power plants, there are many power electronic converters which leads to power quality problems including harmonic noise and voltage swings that decrease the life of the equipment. Shunt active power filters decrease harmonics, voltage swings and the insistence for reactive power from non-linear loads in single phase which is two-wire system and three-phase with neutral which is four-wire system and three-phase without neutral which is three-wire system. Using the PQ theory, the reference compensating current is retrieved. The simulation results verified MATLAB 2015A software. Different MATLAB results are verified during the steady state and dynamic state. The simulation results are verified output voltage, output current, and total harmonic distortions. The keywords used in this paper are power quality, active power filter, harmonics, voltage fluctuations, and reactive power. Introduction of this paper is nowadays electrical equipments has made extensive use of power electronic devices. Applications for power electronics have expanded greatly. Rapid advancements made them technically and financially feasible. These power electronics have several reimbursements, but they as well have the drawback of extracting harmonics and reactive current from characteristics like low efficiency and inadequate power factor. Additionally, they bother other customers and interfere with nearby communication networks. Non-linear loads have extremely non-linear properties and draw non-sinusoidal currents from alternating current mains, which results in voltage and current distortions known as harmonics. A power electronic based equipment active power filter has been designed to simultaneously overcome these issues, such as problems of harmonics and reactive current. Coming to the topology section, the following figure demonstrates the harmonics, currents, reactive currents, fluctuating currents, and unbalanced currents and excessive neutral currents created by non-linear loads may be corrected using shunt active power filter. The optimum option for current-fed nonlinear loads and mixture of current-fed and voltage-fed nonlinear loads with a modest rating is provided by the shunt active power filters. Due to their low price, small size, lightweight, and low losses, PWM-based voltage source inverters are favored for the realization of shunt active power filters. If A, B, and C are three phases, then the three-phase unsymmetrical voltage components VA bar, VB bar, and VC bar are converted to positive phase sequence component V positive bar, negative sequence component V negative bar, zero sequence components V zero bar, and it is determined by the equation V naught bar, V positive bar, and V negative bar is transformed by using alpha by VA bar, VB bar, and VC bar, where alpha is a constant and complex number that acts as a 120-degree segment shift operation. That is, alpha equals to 1 at an angle 120 degrees. And it is represented by the equation e power j 2 pi by 3 equals to 1 by 2 plus j root 3 by 2. And the inverse transformation equation of the above equation is VA bar and VB bar and VC bar are converted into the V naught bar and V positive bar and V negative bar by using alpha. The balanced three-phase system's real and apparent power and reactive power, and it is determined by the 3 times that of the single-phase powers. Three-phase voltages and currents consist of only positive sequence components, which is sinusoidal and also a balanced system. And three-phase voltages are given by the VA of t, VB of t, and VC of t. And the equation 3 shows the three-phase ABC voltages. Three-phase currents are also given by the IA of t, IB of t, IC of t. Equation 4 shows the three-phase A, B, C currents, where positive symbol indicates the positive sequence component. Coming to the control technique section, the following figure shows the complete block diagram of the shunt active filter. The PI regulator in the above figure regulates the DC voltage and generates P loss. These power loss are worn to rectify the faults in the power compensation. Power loss is supplied to load by the active filter, which causes variations in DC voltage, and PI senses the variations and supplies the extra amount of power that is added to the power loss signal, which is equivalent to the P0 bar. And this power is used to meet the losses of the filter, that is shunt active filter. Delta P0 is superseded by the P loss, which is known as power loss. The versatile tools for reactive power compensation as well as harmonic compensation are provided by the PQ theory, which defines the instantaneous, real, and imaginary powers. PQ theory is always considered in a three-phase system, even it is three-phase three-wire without neutral or three-phase four-wire with neutral. The PQ theory is very important when power systems deal with the non-linear loads. When employed as a power compensator, the PQ theory is extremely useful for building power electronic devices. The PQ theory employs alpha-beta naught transformation, commonly referred to as the Clark transformation. The three phases, voltages, and also currents are turned into constant reference frames in this process. The voltages are instantaneous VA, VB, and VC in ABC phases, and V alpha, V beta, and V naught are the instantaneous voltages in alpha, beta naught axis. Transformations are mainly used for controlling DC quantities. This transformation is converting three-phase to two-phase as well as two-phase to three-phase. And the Clark transformation is given by V naught, V alpha, and V beta voltages are transformed into VA, VB, VC voltages. Coming to the simulation results, there are 7 simulation results. Figure 1 represents the three-phase source current with respect to the time, and the figure 2 represents the three-phase load currents and plotted between the load current and the time. Figure 3 represents the three-phase voltages, both as well as voltages and currents, which are plotted against time. Figure 4 represents the reactive power component, which is plotted against time. And figure 5 represents the output calculation waveform. Figure 6 represents the active power component and plotted between the active power and the time. Figure 7 represents the three-phase voltages waveforms. Coming to the conclusion of this paper, we provide a descriptive illustration of a shunt active power filter in this work. A shunt active filter is used to minimize the harmonic and reactive currents produced by the power electronic converters in a power plants. To resolve these challenges, which are illustrated in the control technique section, the IRP theory was utilized. The output waveforms with a filter are displayed in the result section. This paper's primary goal is to prolong the life of the power systems and improve power factors. Thank you.